Welcome to the next lecture, my dear students. So in the previous lecture we have discussed about the arithmetic mean method. So in this lecture we are continuing the population forecasting using different techniques. So that is, in this we are going to tackle the portion where we are having rapid growth. So earlier where we have discussed about the constant growth concept. So if there is constant growth, that means the graph will be like this. For example, if it is a constant growth, then so the graph will be like this. So here we can assume that the dp by dt. So for example, if you take this as p1 at a t1 time, and this is p2 at a t2 time, and this is p3 at some t3 time, okay, at some t3 time. So here dp1, dp2, so this is dp1, so here this is dt1, and this is dt2. So here the slope is constant everywhere, so we have assumed that dp by dt is constant. Okay, so we have assumed like this in constant growth method. But this is only one portion of the graph. Another portion where there is logarithmic growth or exponential. So logarithmic or exponential growth. So where we are having logarithmic and exponential growth, there the graph will be, it's not a straight line, it will be a curvature. It will be having curvature. Okay, so here what happens, so this is p1, this is p1, this is p2, this is p3. Here dp1, so this is dp1, here dp1 dp2 by dt is constant, but here it is not like that. Here what happens is, so the dp1, so it is exponentially growing, so dp1 is less than dp2, and similarly it will be less than dp3, and so on. So here what happens is dp by dt is not constant. Here what is happening, dp by dt is proportional to population at that time. So it is proportional to population at that time. So now what is meant by this? If you look at the progression, if you look at the geometric progression, you will understand this. If you look at the geometric progression, so for example, today's population is P0. Let today's population is P0. Okay. So let tomorrow's population, it should be, let it is A. Let after 1 decade, its population will become A into R. After 2 decades, it become AR of R. So this is nothing but PT. Okay. So this value, so this is a constant. So now, so P2, okay, this P2 is proportional to the earlier population PT. So it dependent on this value. So similarly, third decade population, if you take third decade population, it will be equal to AR square multiplied by R. That means again this is PT for this. This is PT. So the future population is dependent on the present population. Similarly, so that is why here we take it as, so here in rapidly growing cities or exponential growth condition, so there we take that dp by dt is proportional to pt. So dp by dt is proportional to pt, and the proportionality, if you keep a proportionality constant, then dp by dt is equal to k into pt, is equal to k into pt. So this is the case when we are having the exponential growth. See, this exponential growth we will discuss in many subjects and also many times in environmental engineering also, because all the things happens in a exponential manner only. Either it may be increasing or it may be decreasing. Everything will happen in a exponential manner. We assume that it is happening in logarithmic manner only. For example, if you take the killing of microorganisms, if you take the decay of BOD, if you take the degradation of oxygen or reoxygenation curve. See, why I am saying all these things at this point, because everywhere we assume that all are happening exponentially. Either it may be exponential increase or it may be exponential reduction. So we assume all the things will happen in a logarithmic manner. Okay, so here this logarithmic concept we use many times in this environmental engineering. So everywhere the concept will be the same. The calculation part, the mathematical part will be same. Only thing is what are the parameters we are considering. So if you are taking population versus time, then it is population curve, logistic curve. If you are taking oxygen versus time, then it is oxygenation, deoxygenation or reoxygenation curve. If you are taking BOD with time, it is BOD degradation curve or BOD curve. Or if you take oxygen DO with time, so oxygenation I already told you. If you are taking that microorganism versus time, then microorganism called as a killing rate of microorganisms, that we understand. So all these things, or else if you take about chlorination versus time, so what is the amount of chlorine being consumed. So all these things, whatever we take with different parameters, but the graph will be same, the mathematical calculations are also same. So that is why here I am using that mathematical part for the sake of population forecasting when there is exponential growth. Okay, so when there is exponential growth. So exponential or logarithmic, where dp by dt is proportional to population, present population. Okay, so here I will keep a proportionality constant of k. So I will take it like this. So it means dp by pt is equal to k into dt. So integrating it on either side, keeping the limits of p1 to p2, and the time is t1 to t2. Okay, now here it is ln pt, the limits of p1 and p2, and this is k into t, the limits of t1 and t2. Okay, now this is ln p2 minus ln p1 is equal to k into delta t. So this is ln p2 by p1 is equal to k into delta t. So p2 by p1 is equal to e to the power of k into delta t, and p2 is equal to p1 into e to the power of k into delta t. So this is the population. This is the population when we know the rate constant. This k is called, so p2, or we can say this as pn is equal to p naught into e to the power of k into delta t. So we can also write the same equation like this, where pn is equal to, so future population P naught is latest known population, P naught is latest known population, and K is rate constant. So this term will come everywhere. Rate constant means this is a slope of the curve. See, it indicates how the curve is varying. The rate constant depends upon the pattern of the curve. Okay, so pattern of the curve, rate constant. So delta t, see, rate constant may have any unit. Rate constant either we take per year or decade. Okay, we can take either per year or per decade. We can take any value. But subsequently delta t should be time in year or decade. So you need to look at the rate constant value. So if the rate constant they have provided you per year, then you have to substitute the time per year. Though you are having a decade data with you, though we have data in decades, but the rate constant we have derived it per year, because here k into delta t, it should be a unitless value. So if it is per year, then delta t should be in year. If it is per decade, then delta t should be in decade. You need to be very cautious about substitution of k value and delta t value. What are the units of k? It was given in the question. The same units you need to adopt for delta t also. Otherwise, you will get a wrong answer. Okay, please be cautious in that location. Okay. Now, so this is one way of deriving the future population using a kind of logarithmic approach, using integration technique. So there is another technique, that is progression technique. So if you arrange the data, this is one kind of data from the graphical representation. When you are having a data in the form of a graph, then you will get a rate constant from that graph. So there, if you are having a rate constant, this kind of approach we follow. If you are having a past population data which is segregated in the form of numericals, in the form of a number format, then this formula may not be suitable, because again we need to plot that on a graph, and we need to derive this k value from that graph, and then we have to use this one. So instead of this, it will be if you do this much procedure, it will be lengthy. So there is another method also which will be useful when you are having a past population data with you. Then that is a progression technique. So geometric increase method of forecasting. Let us see that method also. Geometric increase method. See, I told you already. So here in geometric increase method, dp by dt is proportional to pt. Okay, that means, so when the population is like this, ar square, ar cube. So this kind of pattern is nothing but, this pattern is explaining that dp by dt is proportional to pt. So now for this pattern, so this is the first year population's 10th year. That means first year population, first decade, second decade, third decade, like you want it for nth decade. So you want the population, future population of nth decade. So nth decade, if it is p naught, and this is p1 and this is p2 and so on, it will be pn. So the nth term of this geometric progression or geometric increase method will be our future population, the nth term. So how to write this nth term? So nth term is equal to p naught plus into 1 plus r by 100 whole to the power of n. This is the formula. This is the formula for finding the nth term of a geometrical progression. This is the formula to find the nth term of geometric progression, which is the population of nth decade. Okay. Now, here what is P naught? So P naught is latest known population. It is latest known population, and Pn is future population. Future population. R is growth rate. Growth rate. Okay, N is number of decades. See, again we are having data. This R is for decades. Here the R is for decades. So that is why the N value should also you substitute in decades, not in years. Okay, you should substitute in decades. Okay, now so how to calculate R here? It is a very important thing, because so P naught is latest known population. For example, if a data is given to you, for example, I told you 1990, let the population is P1. 2000, let the population is P2. So 2010, let the population is P3. Okay. So 2020, let the population is P4. So then from this, if I ask 2050, then how to calculate R first? Because P naught is P4, because P naught is the latest known population. Pn is population at 2050, that is future population. N is number of decades. So 2020 to 2050, there are 3 decades, because a decade is 10 years. So 50 minus 20, 30 years means 3 decades. So N value is with us. Pn is what is the value we need to determine. P naught is latest known population, that is P4. Then where is R? So R is not visible directly, we need to calculate it. That is why it is difficult to understand. So R is nothing but, see, growth rate, right? So growth rate means here dp. So whatever the value P2 minus P1. So what we have did there, dp by p, isn't it? So here what we have did, so dp by p is equal to k into delta t, isn't it? This is what is our derivation we have did. So delta t, if it is 1 decade, delta t is 1 decade, then what is k? K is nothing but dp by p. dp by p is k. So dp by p means, so dp, that means p2 minus p1 by p means the first reading, initial reading, that is p1. Okay, p2 minus p1 by p1, that is dp1, that is dp by p, that means r1. I can take it as r1, or k, here we are taking it as k, but in this formula this k is nothing but r. Okay, so here this is what? This is r1. This is r1. Similarly, there will be r2 here, there will be r3 here. Okay, so r1, r2, r3 we can determine using this formula of dp by p, where delta t is 1 decade. So now we are having r1, r2, r3. Okay, then how to calculate r? Uniform value of r, average value of r. So there are 2 methodologies again to find r. See, either you can find this r1 plus r2 plus r3 by 3. So this is one method. Or you can do arithmetic mean. This is arithmetic mean. So either you can do geometric mean, that means cube root of R1, R2, R3. So the R percentage, the growth rate percentage, you can either take as an arithmetic mean or you can take it as a geometric mean. Then which one do you follow? See, generally for design purposes, we prefer arithmetic mean, because R percent from arithmetic mean will be greater than R from geometric mean. Okay, so that means this R value will be larger. So that means if this larger value, if I keep here, it will give more population. So my design will be on safer side. If there is anything, any errors, if I commit in the calculation of the population, in forecasting of the population, will somehow rectified by taking a larger value of R. So that is why, to be on conservative side, so we generally assume this R value from arithmetic mean method. But you can adopt anything. So you will get the nearby values only. You can try in the questions. So either you can take arithmetic mean or you can take a geometric mean. So if it is a question, then go with geometric mean. If you are designing a system, then go with the arithmetic mean. So if you are solving a question, then go with geometric mean. So if you are doing a design, go with arithmetic mean. Am I clear? So now we have, so in this formula, everything we can determine now. Everything we can determine, simply substitute the values. So you will get the population of future in the form of geometric increase method. So this is geometric increase method. And next method is incremental increase method. So what is meant by incremental increase method? See, whenever the graph, either it may be a straight line or it may be a curve, but it should be continuous. To be applied a arithmetic method, or to apply geometric method, so the curve is continuous. It is not having a wave nature. So if the curve is having a wave nature, so it is looking like a wave. It is going up, going down, and going up and going down. So it is having, the population growth is having a very erratic behavior, very different behavior, which a proper pattern it is not following. Then in that case, we cannot apply the arithmetic mean or we cannot apply the geometric mean. So that means when the curve is not taking a shape, proper shape, then in those cases we use the incremental increase method, where the growth rate is increasing and decreasing, but there is growth, but the growth rate is not constant. Growth rate is varying. So incremental increase method. Incremental increase method. For example, if you take a graph, okay, population versus time. If you take population versus time, the graph is like this. If the graph is like this, then in these cases we cannot have a proper shape, proper analysis we cannot do. See here, what I can do is, so for this data, so there will be a average value. So let this is X bar line. Okay, so let this is an X bar line. So from this X bar, so how much the data is deviating. So let this data deviation is, let this is Y1, let this is Y2, let this is Y3, Y4, like that. So here So to enhance the accuracy of population forecasting, I am going a step ahead. See, earlier I was confining to only up to this X bar line. Now I am moving on to the next level of accuracy. So if you look at a vernier calipers, what we will do? So generally we take only up to 2 decimal, but in vernier calipers we take up to 3 decimal because we are introducing another scale, another reading into it. Similarly here also, earlier we have confined it to the level of up to this, but now I am moving up and down also. That means I am enhancing my accuracy of forecasting of population, because here the population is very erratic. I cannot confine myself to X bar. See, those curves, though I am using the arithmetic curve also, arithmetic increase method also, I assume that it is a straight line, but it is in actual, it is not a straight line. It is also having a curve. See, if I take arithmetic mean method, I just take it like this. But in reality, it may also have small curvatures like this. We don't know. But what we are doing here, these values are very negligible. So these values are very negligible. That is why I am assuming that it is X bar only directly. But if these values are increasing, this value, the amplitude of this wave, if it is increasing, then what I can do, I cannot neglect these values. I cannot neglect these values from considering into our population forecasting. If you don't consider, then the value will not be an accurate one. So that is why here these values, if they are not negligible, then we need to consider them also into account to forecast the population. So that is what I am doing here. That is what I am doing here. So now here, so that is why what we are doing is, so we are going ahead to one step extra to also incorporate the value of y bar. So here the population after n decades, or the future population, it is defined like this: Pn is equal to P naught to n into X bar. This was the arithmetic mean method. This was the arithmetic increase method or arithmetic forecasting technique. So here what I am doing, I am giving some place for this y1, y2, y3 in the form of y bar. So I am also taking the average of y, that is y bar, and the coefficient here is n into n plus 1 by 2. So here this is the formula for incremental increase method to use to forecast the future population when the population, the logistic curve, is having a erratic behavior. Okay, so Pn is population after n decades. Population after n decades. And this X bar we already know, already we have calculated X bar. The Y bar is, see here during the calculation of the Y bar, you need to consider the sign. For example, so here if it is coming as a 5000, okay, here this one is going down, that means let it is minus 3000. It is minus 3000. Let this is again 4000. Let this is again minus 6000. For example, okay, so these are the values I am having. Then for these values, the Y bar will be 5000 minus 3000. Okay, 5000 minus 3000 plus 4000 minus 6000. So this is 9000 and this is also 9000. That means Y bar is 0. So Y bar should be sum of all the values duly considering the signs. So you are not supposed to neglect this minus here. You need to add it in the form of minus only if it is going down. If it is going down, okay. So that is what you need to consider. You need to look into during the calculation of Y bar. Okay. So for our explanation, let us take it as 5000. Okay. So here in this case, y bar will be equal to 5 minus 3 or else 9 minus 8, that means it is 1000. Okay, in this case it is y bar is taken as 1000. Okay, so likewise we need to calculate y bar. You need to take the minus sign into consideration. You need to take the minus sign into consideration. Okay, and the average, anyways we will take the average. So here how many readings we are having, so divide it with the number of readings, then you will get the average value. Then you will get the average. Y bar is equal to 1000 by 4. Okay, so likewise we need to solve this incremental increase method to forecast the future population. So y bar is how I have explained it. In the same manner we need to find the y bar value, and n is the number of decades. Average value of deviation, and n is the number of decades. Okay, and x bar is average growth. So this is incremental increase method. So next is decremental growth method, or decremental growth rate method, or decremental increase method. So next method is decremental growth method. Decremental, that means when the city is approaching to its saturation, then what happens? It cannot accommodate any growth further. In that case, what happens? In that case, the growth rate will present, but it is decreasing. For example, this decade the growth rate is 10%. Next decade the growth rate is 8%. That means there is a declination of 2%. In the coming decade the growth rate was 7%. That means there is a declination of 3%. So growth is happening there also, but the growth rate is declining. Growth is happening, the growth rate is declining. That is nothing but decreasing growth method. Okay, so in decreasing growth method also population increases, but the growth rate decreases. Okay, decreasing growth method. In decreasing growth method, so population increases but rate of growth decreases. Here if you see, when you look at the graph, so when it is nearing to the saturation, what happens? So here dp by dt reduces. So here this one is reducing. If you observe this graph, it is approaching towards the saturation. So this is PS. Okay, this is PS, and this is PT. Anywhere. So it is proportional. So this here dp by dt is proportional to PS minus PT. So here how much scope is there to grow? How much scope? This is the scope to grow, isn't it? This is the scope. If it is reaching to saturation, there is no scope of growing. So if it is not reaching yet, so there is a difference between the present population and saturation. So the difference decides the growth. The difference decides the growth. So that is why here in decreasing growth method, so dP by dt is proportional to PS minus PT. PS minus PT. So here, for example, so if you know a population, so let the population of latest known population is P naught. Let latest known population is P naught. Okay, so the growth rate is R%. Growth rate is R%. And decreasing growth is D%. So let the decreasing growth is D%. Okay, then population after 1 decade, population after 1 decade, okay, that is P1 is equal to P naught plus, so P naught is already existing population, P naught plus R naught should be the growth, actually R naught into P naught, so this is R naught into P naught by 100, so this should be the growth. If you take a geometric method, so what is Pn? Pn is P naught into 1 plus R by 100 whole to the power of n. So if the n is 1 and this is R naught, then it should be P naught plus R naught P naught by 100, isn't it? So this is what is PT. This is what is Pn or PT, whatever it may be. Pn or PT, whatever it may be. Now, so that is what is the geometric increase method formula, but here it is decreasing. So this was the intended increase, but there is a decrease percentage of D. There is a decrease percentage of D. So I need to remove this one from the population also. So there is a rate of increase as well as there is decrease. D naught P naught by 100. So if you mix up this completely, then it will become P naught into 1 plus R naught minus D by, so let it is not D naught, let it is D by 100. So this is a formula. This is a formula where R naught is the growth rate, okay, where R naught is the growth rate and D is the decreasing rate. So where R is the, let us take it for uniform value, let us take it as R. Let us take it as R. R is the growth rate, R is the growth rate and D is the decreasing rate. So R is also an average value, D is also an average value. So as I told you, this is also an average value, R1, R2, R3, there will be different values. If you are using it completely for all the data, you need to take an average value of R as well as average value of D. Okay, average value of D. So now, so this is for only 1 decade. If it is for nth decade, if I want to find it for nth decade, then here for 1 decade there will be 1 decrement. If you are doing for 2 decades, there will be 2 decrements. If you are doing for 3 decades, there will be 3 decrements. Are you able to understand? So if you take 1 decade, see, if you want to find for n decades, so if with a known population of, latest known population of P naught, then the first decade the population will be 1 plus R minus D by 100. So this is the population of first decade. This is the population of first decade. So for the next decade, so 2 decades, second decade, so this will be P1 now. This will be P1. So this will be P1 for the first decade. So this is the population. This is the latest known population. This is the first decade population. So this is P1. So this P1 multiplied by 1 plus R minus, see this R is for the first decade. Now this is the R minus D. So this R is for the first decade. If you want to find the second decade, so this R minus D will be the rate for the second decade. So this is the rate, minus D is a decrement. Are you able to understand what I am saying? Are you able to understand what I am saying? See, P naught, latest known population, is having a growth rate of R. Listen carefully. Latest known population is having a growth rate of R. But after one decade, along with the growth rate, there is a decrement in the growth also. Along with the growth rate, there is a decrement in growth also. How much is the decrement? D is the decrement. So for first decade, what is the rate of growth? So this is the rate of growth, as well as decrement is also there. So the net growth. So simply, if you are earning a salary of 50,000 and your expenditure is 25,000, so net is 50 minus 25. Here this is also 50,000, this is 25,000 which is going out. Now this is the net growth rate. So this is the net growth rate of first decade. This is net growth rate of first decade. Now if I wanted to find for second decade, now this one, take this as a unit. This is the population of first decade. This is the population of first decade. And this is the growth rate of first decade. So this one will be the growth rate for the second decade, but there is a decrement D. So the net growth rate for the second decade is this much. The net growth rate of the second decade is this much. So this is previous population. Now this is the growth rate. So that will give you the nth population, decade of second decade population. Similarly, if you are going for third decade, so this will be your second decade population. This will be your second decade population, 1 plus R minus 3D by 100. 1 plus R minus 3D, 1 plus R minus 3D by 100. Similarly, if I want to find nth decade population, 1 plus R minus ND by 100. When you don't know the n minus 1 population, this is nothing but, so if you are doing for a nth decade, so this is nth decade factor. This is nth decade factor. So this is nothing but, up to this is nothing but P n minus 1. Isn't it? So listen carefully. Forget about this part. Forget about this. Don't look at this part. Only look this part. Only look this part. This is P naught and this is P1, right? So this is P naught and this is P1. Don't look this portion. Only look at this. So if you know the latest population, that means if you want 1 minus 0 you are having 1, you want the decade 1, but you are having the value of population of 1 minus 0. Then simply P naught into 1 minus R minus D. If you want 2, but you have P naught, not P1, you have only P naught. The latest known population is not of the previous decade, it is of previous decade. Then you have to use this formula. You have to use this formula. Are you getting me what I am saying? Instead, if you are having P1, here what I am saying, I am not giving you P naught, I am giving you P1. I have asked you P2. I have asked you P2. So P1 means what? This is P1. This is P1. So the P2 will become this. P2 will become, so the P1, so this is P1, right? So this is P1 actually. P1 into, so for the second decade, so this will be the value 1 plus R minus 2D by 100. So what I am saying, if you know Pn minus 1, if you know Pn minus 1, then Pn minus 1 into 1 plus R minus Nd, 1 plus R minus Nd, so N is the number of decades. N is the number of decades. After 5 decades you want, then put 5. After 10 decades you want, then put 10. Okay, so here Pn minus 1, so I can also write this as, this formula as like this also. So this is Pn actually, this is Pn and this is P naught. So this is one formula, this is one formula. And if I know Pn minus 1, this is Pn minus 1, then Pn is equal to Pn minus 1 into 1 plus R minus Nd by 100. So this is also another formula which I can use if I know Pn minus 1 completely. Okay, Pn minus 1. So this is decreasing growth method. This is decreasing growth method. So not that much important for the GATE examination. Not that much important for the GATE examination. So anyways, this is also a concept which needs to be understood. So that is why I have explained you. Okay. So now in the next class, we are going to learn the rest of the population forecasting techniques and rate of demand topics and all. Thank you so much.